Good morning, everyone. Can you hear me?
Yes, and we can see the inelastic collision screen.
Okay, good. Thank you. Okay, so today we want to look at the concluding part of our chapter 9, and we'll start with the inelastic collision. We'll have elastic and inelastic collision as we've seen in our last lab class, but the elastic collision, to treat the details of the elastic collision, we need to understand some basic principles about energy. So we'll meet that again in chapter 10. We'll mention the elastic, but for now, we'll focus on the inelastic collision. Okay. The inelastic collision, also we saw that type of a typical inelastic collision in the lab experiment we did. A collision in which two objects stick together and move with common final velocity is called inelastic. Now we'll have perfectly inelastic collision where they will exactly move with common final velocity. All right. So when they stick together and they have common final velocity, we describe such collision as inelastic. Let's see an example from the image before us. We see the objects. We see the objects 1 and 2 coming in opposite direction with initial velocity in the x direction as v1xi and the v2xi. Before their collision, you can see they're moving differently. Okay, so they collide and stick together. Then they move together. So they moved with common final velocity. So the masses combined, and then we'll have common final velocity. This is a typical example of a perfectly inelastic collision. We'll have some other examples, like when you hit a clay ball, throw a clay ball to the floor, you see that the clay ball does not bounce back. It does not bounce off the floor. It gets stuck to the floor. Such kind of collision is inelastic. But whenever there's a collision and the object bounces apart, we say such collision is elastic. All right, so that's the major difference between inelastic and elastic. For elastic, they can change the direction of motion, but they don't stick together, they don't move with common velocity. But for inelastic, they stick together and move with common velocity. We have other examples of inelastic collision, like when a bullet is shot to a tree and the bullet is embedded inside the block or inside the whatever it is shot into. Such combination is also inelastic. Okay, so we have seen several examples of elastic collision when we were describing impulsive forces. We see a collision that the two objects has to move apart. Okay, most of those examples, they are elastic collision. So let's see, take an example on inelastic collision. In assembling a train from several railroad cars, two of the cars with masses 2.0 times 10 raised to the power 4 kg and 4.0 times 10 raised to the power 4 kg are rolled towards each other. When they meet, they couple and stick together. The lighter car has an initial speed of 1.5 meter per second. The collision causes it to reverse its direction at this speed, 0.25 meter per second. The question is, what was the initial speed of the heavier car? So let's make a virtual presentation of the question given to us. We have two cars. Car one, we're assuming now that car one, which is the lighter one, has this mass 2.2 times 10 raised to the power 4. And then car two has this mass as given in the question. The initial velocity of car one was specified to be this value, 1.5 meter per second. They are moving in opposite direction, but when they met, they got stuck together and they moved with common velocity, the masses combined towards the left direction. And the velocity of, that's the final velocity, is given to be 0.25. But we'll put 0.25 here to indicate the direction of that velocity, which is towards the left. Okay, and the question is now asking, what is the initial velocity of this heavier car? All right. So we have been discussing momentum. We're going to use that, but in this case, with the understanding of the inelastic collision, that is, understanding that the final velocity is actually a combination of their mass, and then the two of them will have a common velocity. Okay, so coming from the law of conservation of momentum, which we stated as this, that the momentum at the final is equal to the momentum at the initial. And how did we arrive at this? We stated that the total momentum of an isolated system is constant. That is equal to 0. So by the time you plot the momentum of the final, that's change in momentum, and you move the initial with the minus across the sign of that is, will have something like this, equal to 0. So we'll have PF to be equal to PI. This one crosses the sign of equality. Okay. So from our understanding or definition of conservation of momentum, the final will be equal to the initial. So the final momentum, we know momentum is P equal to mv, right? So the mass at the final combined with one velocity, so we'll have m1 plus m2 being equal to the separate masses before the collision, m1 v1 m2 v2. We're asked to look for this. Okay, so we'll have to make it the subject of formula in this expression. So making this the subject of formula in this expression, first we'll move this one to cross the sign of equality, so it becomes negative. That's how we got this negative sign here. So we'll have m1 plus m2 v final minus m1 v initial for v1 initial, and the whole thing happened in the S plane, so we didn't have to present the y component of it. So divided by the coefficient of v2 initial, which is the M2. So we just substitute our values as given into the equation here. So we'll have the mass plus the two masses will give us 2 plus 4, which is 6 times 10 raised to the power 4. Then we'll have the V final. Remember the V final. It is important to know the direction because the direction in the question was not given to us as minus, but because from the presentation we can see the direction. So we got the minus, okay? So that's how the minus came in. Minus the mass for M1 and the speed all over the mass for M2. So we'll have the final velocity of boats to be minus 1.1 meter per second, indicating that it's moving to the left. And if we see the final visual presentation of the truck, we can see that it's moving to the left, which is bringing the negative direction. So it makes sense because the lighter car could not push or change the direction of the heavier car. They have to move together with one velocity towards the direction or initial direction of the heavier car. Okay. This example, I believe, is straightforward. So let's quickly look at these two examples given to us from the understanding of what we just did. Okay. Look at these two objects. Their masses are given and their velocities are given. Okay. They collided and stuck together. They moved with the same velocity. But we want to know the direction. Okay. Is the direction, I'm going to launch a poll, you quickly get to solve it to define the direction. Don't just assume what is presented here because it's a question. It's that you agree or disagree. Okay. So what will be the direction of this? And I expect response from everybody. I gave you 2 minutes to do that. Don't just pick an option, make sure you solve it to know. And when you are solving, note the direction. This one, when solving this one, for example, note that it's pointing to the left and use the minus sign to solve, okay? Let me see how many persons do we have today? 26? Because some of the objective questions you may see in this test too come in this form. And sometimes we put this kind of twist to questions so that we'll be able to know if you really solve to get your answer or you just read and do guesswork. Okay. I'm waiting for, I just have 19 response out of 26. Four more persons. Okay. I'm waiting for 3 more inputs. 2 more. Who has not responded? It's important that you respond, because if you don't, the implication is that you connected to the class and walked away. But there is no other way to know if you're actively participating in class or not. Okay, so if I don't see your response, it means I have active 24 persons present in class today. All right, I'm ending the pool now. Okay, thank you. So see that majority of us said B, some of us said A, and some of us said C. So if we will solve this out to be part of our revision class soon, or if we have time at the end of the class, we'll come back to solve it together. One moment. Can you still see the pool?
You can see the like where the choice is the move to the right as shown, move to the left or at rest, and then the diagram, like your PowerPoint slides we see.
Okay. Thank you. Okay, so let's move forward to the next thing we have to discuss today, which is momentum and collision in 2 dimensions. Now, in our last class or previous classes, after we discussed linear collision, we move on to describing 2-dimensional motion, right? Sorry, I thought this linear motion, sorry. We discussed 2-dimensional motion, and we're able to see that we had comparison of many of the parameters in the linear motion also present in the 2-dimensional motion. In 2D motion, we're simply talking about motion that can actually be expressed or in the Y and S component. Okay, and that was what led us to the discussion of resolution of vectors, where we have to decompose them to the X and Y plane. It's the same idea we want to bring in here. How do we, because we have just seen the explanation of momentum in the linear, either S plane or Y plane. What happens if we have a motion that can actually be described with 2-dimensional motion, especially motion that are not just on a straight plane? How do we describe that? Can we also bring in the ideas we have into this? The answer is yes. We have that momentum is a vector and it's going to move in the direction of velocity. So if momentum is a vector and we'll have a system where we'll have more than one object, we can actually say the final momentum is going to be the sum of the various momentum as we stated in our last class. Okay, so if we apply this same knowledge to the 2D problems, we'll also arrive at the same conclusion, but in this case, we'll have the option of expressing the x component equation and the y component equation. When we're solving the linear ones, we look at the motion, we just present the equation that applies. Like the example we just concluded, we just presented the s component. Now, specifying that it's s component tells us that if that motion happens to have the y component, or can be described in the s and y plane, that is 2D, 2 dimensions, we'll be having the y component part of it. So we'll just take an example using the same idea because the same rule applies. The only difference is that for problems with 2 dimensions, we'll have to solve for x and solve for y. Okay. So let's take this example of the peregrine falcon. Peregrine falcon is this kind of bird that go after prey in motion. Okay. So the peregrine falcon often grab their prey in flight. So a falcon flying with the speed of 18 meters per second swoops down at the angle of 45 degrees from behind the pigeon flying horizontally at the speed 9 meters per second. Now the falcon has a mass of 0.8 kilogram and the pigeon has a mass of 0.36 kilogram. The question is, what are the speed and direction of the falcon when it's now holding the pigeon immediately after the impact? So before the impact, we have the virtual representation of this question here. Before the impact, they were both moving differently. The pigeon was moving obviously from the picture towards the left, which is the negative s direction horizontally, as stated in the question. Okay, although the question did not specify here that it's moving to the left. All right, but let's picture that the pigeon is moving to the left, and then the falcon was above the pigeon, just swoops down at the angle 45. Okay, so represent the angle where it swoops down to meet this pigeon to be theta, which is 45. And then we'll have its initial velocity given and the initial velocity of the pigeon given. So bringing out our parameter, we'll have the mass of the falcon, the mass of the pigeon, the angle. Then we'll have the initial speed of the falcon and the initial speed of the pigeon. After impact, they combine together, they are moving together at the same speed. So that should influence also the expression of our parameters. Okay, so after impact, we represent the angle with alpha, and then we'll have the final velocity for the s component and y component and the resultant velocity. Okay, so now let's bring out the component expression. We have seen from this description that it is a motion that is not just in one plane, especially that of the falcon. It is actually the motion of the falcon that brought in the idea of 2 dimensions into this question. For the pigeon, it was moving on one plane, the horizontal S plane. So we'll have the expression for the momentum, initial momentum in the S component. Now the initial momentum in the S component, because there are 2 objects, will be the summation of the individual momentum of these objects. So we'll have the mass momentum, the P equal to mv equation. So we'll have the mass of the falcon and the initial velocity of the falcon plus the mass of the pigeon and the initial velocity of the pigeon to give us the initial component of this question in the X plane. Okay, so Substituting from this expression of the actual values, we'll see that the the velocity of the falcon in the S initial plane, because it is a 2D motion, we'll have this X and Y expression. So we'll have, for us to use this course, remember S plane, which is this plane. So we'll have the adjacent over hypotenuse expression to give us, the minus is telling us the direction, okay? So we'll have VF for falcon, velocity of falcon, cos theta, the angle here, adjacent over hypotenuse, brought in the cos, okay? So we'll have our V initial for the S plane to be this, plus for the pigeon is straight, but the minus came because it's going to the left as well. So we see the left representation with the minus. So this is the S component. If now put in our parameters provided, the mass, and then VF that was given in the question, but now carry negative because of the direction, cos 45, because that angle is given, plus the mass of the pigeon and the initial velocity of the pigeon. So we'll have the value for the initial momentum to be this in the S plane. Okay, so we will also do a similar thing for the Y plane. For the Y, we bring out the component, the momentum component for that as well, which is the sum of the, remember we're still dealing with the initial momentum, initial X component and the initial Y component, initial momentum. So for the S component, a Y component will have the Y direction of the pigeon is 0. So, but expressing it is going to be the summation of the Y for pigeon and falcon. So for pigeon, it's only moving horizontally, so it didn't have the Y component. So we only have the Y component for the falcon, which is this Y component, okay? And that is opposite over hypotenuse, and that is sine. And the direction is negative or towards the left. That's how the negative came in. So substitute our values like we did in the S component with the mass, the velocity, then the sine theta, which is sine 45, to obtain the momentum in the Y direction to be minus 10.2 kilogram meter per second. Y for the X was minus 13.4 kilogram meter per second. So we'll have the values for our initial component for S and Y, okay? So the S component of the final momentum is then, because note the word, we finished the initial, we're doing the final now. The final momentum, they both combine their masses and move with common velocity, right? Remember the question asked us to look for the speed and the direction, okay? So for the final momentum, the S component will be Px final, the combination of those two masses and their common velocity for the X. So from the conservation of momentum law, we have that the final for the S plane now will be equal to the initial for this momentum to be conserved. So if P final is equal to P initial for S component, and we've already seen that P final in the S component is this, so we can actually equate this to this. So we'll have M1 plus MPVF equal to PSI. And we now made this V the subject of formula because that's what we asked to look for. That's how we arrived at this. So we'll have MF plus MP Vx final being equal to Px initial. So if we make this the subject of formula, we have to divide by this component. Okay. So dividing by this component, we'll have the sum of these two, which is the sum of the masses given. Pi, momentum, we solve for that to be 13.4 kilogram meters per second. So we now have a final velocity to be minus 11.6, telling us that they continue their motion towards the left. Okay. So similarly, we solve for the y component as well. So we have the same way we applied the first case, for the y component, the final being equal to the initial, and we also have the final being the sum of the masses and the velocity in the y direction. And we did the same thing, made it the subject of formula to get this equation, substitute our value with the answer we got for the py to obtain the velocity, final velocity in the y component to be minus 879 meters per second. So we have the y and the s component. So the question asks us to look for the direction because we know the magnitude of the velocity, but we have to express the direction. And to express the direction, we have to bring in the angle because it was actually the angle that gave us the definite direction in the first case for the initial. Okay, so since we have the component for the x and the y, we can actually get the direction for the second one, which we represented with the alpha, that is the new angle, to be tan inverse for y and x, that is the value this over this. Tan inverse of both, the minus took off the minus, so we have 37. All right. So the falcon actually got the pigeon at that angle 37 degrees, and they moved together with the same velocity. All right. So the magnitude of the final velocity for the two, if we have the x and y component, we will now use the Pythagorean theorem to arrive at just one value that we have to put as the final velocity. Okay. So if we use the Pythagorean theorem, we'll have for v to be v final for the x squared, the squared will take care of the minus. Okay. Minus times this, this times this itself will become plus, this times this will be plus, to give us the final as 15 meters per second. Okay. So we have the angle, we have the final velocity, we can actually describe the direction. And also with the understanding that momentum is conserved, it helped us to arrive at this final presentation of the falcon's motion. We see that the falcon actually descended towards the pigeon. So the falcon, which is on the SY plane, had to descend below the horizontal line to get the pigeon at the angle 37 degrees. And then the momentum of the pigeon and the falcon combined and moved in the same direction. Okay. And from the law of conservation of momentum, it simply means the momentum of the system remained constant, which is typically equal to 0. Or some persons will say the final momentum did not exist. Two of them had to move. Okay. So we see how We took step-by-step understanding of what we know about momentum in the linear plane to solve the problem in the 2 dimension. What is the main difference here? We had to solve for the S component and solve for the Y component, combine the two to present one velocity. That is simply what we did. Okay. So let's move to another interesting part, which is the angular momentum. Now, we notice that the concluding part of this lecture is actually talking about the understanding of what we did in the S plane being replicated in what we did in the one-dimensional state or one plane being represented in 2 planes. Okay, like we did in our previous studies, we're able to bring in the analogies of the ideas for the expression of the parameters describing motion in the linear plane to describing motion in a circular or rotational state. Okay, so when we make the statement, the momentum of an accelerated system is conserved. In terms of circular rotational motion, it implies that the Newton's first law holds for single objects. That means the statement that momentum is conserved means the first law for single object in a rotational state. And the quantity that we use to express the idea of momentum in a circular rotational motion is what we call the angular momentum. Okay, so what is the Newton's first law? The Newton's first law says an object will continue in its, like we just say, it's like the law of inertia, in a state of motion at constant speed or in a state of rest, unless it is acted upon by an external object. That is what we mean by, for a single object, the momentum is conserved. All right. So we bring in that idea to understand exactly the expression or the equivalent expression for the momentum, angular momentum. All right. So the same analogy that we used to derive the angular velocity, angular acceleration, and net torque is what we want to extend to describe the angular momentum. So let's see an example. If you're pushing a merry-go-round at the edge, that is at the target of the circle, which is the very edge of the merry-go-round, as we saw in the initial picture for that child pushing that merry-go-round. The child is actually doing what? Applying torque at the rim or the edge of that circle. Okay, so if the child pushes harder and at a longer time, we will notice that the velocity will increase. All right, and if the child decides to add or push at constant torque, the acceleration is also going to be constant. Okay, which means the acceleration will be 0. All right, and from that analogy in our last class was where we now derived the angular acceleration expression to be alpha equal to net torque over moment of inertia. All right, and you know the expression for moment of inertia, right? Remember this in our last class. Okay, so when we just write it as this, you should know each of their components. Torque is a kind of force, the force equivalent for rotational motion. Alpha is the acceleration equivalent for rotational motion, which we call angular acceleration. And then we'll have I to be the moment of inertia. So for that merry-go-round analogy, we have this expression. Now, the angular acceleration is actually defined as the rate of change of angular velocity. So we can actually express acceleration as change in angular velocity, which is W, it's not W omega, then change in T. So if alpha is equal to this and alpha equal to this, we can actually equate torque net to be change in W over change in T. So that's how we got this equation, equating the two alpha. So if we equate the two alpha, we have this expression. Then if we make it a linear expression, cross multiply, T multiply with torque, we have this. I multiply with angular velocity, we have this. Now, if you look at this presentation critically, and you already know torque to be force equivalent in rotational motion, time, then we'll have initial moment of inertia to be mass equivalent in rotational motion, and the V. We can see that in linear motion, it is actually this expression, right? And you know that the expression here in linear motion is what we describe as our change in T. Therefore, we have a kind of representation for our angular momentum equivalent. All right. So we see that L, which is the symbol for angular momentum, is actually from this expression equal to this. So we'll have your L will now be torque change in T, and that this means L, okay, which is equal to IW. All right. So we'll have this expression, therefore, as the angular momentum for an object with the inertial I in a rotating uh, motion or rotational motion, and our W means our angular velocity. The unit for angular momentum is kilogram meter square per second. Okay, so we can see the linear equivalent in the rotational dynamics. The expression PMV actually means this PMV, okay, actually means in the rotational dynamics to be L, which is angular momentum equal to the moment of inertia, product of the moment of inertia and angular velocity. Okay, so we see everything we have or known in the dynamics of linear being extended to the rotational. Okay, so let's quickly also see how then we're going to describe the law of conservation of angular momentum. Since we have described the angular momentum, the same thing applies, okay? The initial is going to be equal to the final for them to be conserved. So it simply means that the implication of that is this expression, we have said it, change in L is actually tau change in T. And that means the equation means that the change in angular momentum for an object is proportional to the net torque. By the time you apply the constant of proportionality, we brought in the change in T. All right. So the net torque is directly proportional to the change in angular momentum, and the T acting there as a constant of proportionality. So the statement captures the conservation of angular momentum as that the angular momentum of a rotating object subject to no external torque, that is when the external torque is zero or is constant. The final angular momentum, which is your LF, is going to be equal to your initial angular momentum. So we see that the conservation law is also similar to that which we have as the P final being equal to the P initial. What's the difference? We just bring in the angular to specify that we're describing a rotational motion. Okay, so because angular momentum is also a vector quantity, it has direction. All right, so we will have that the sum of the initial, if there are going to be more than one in a system of describing more than one object, it's going to be the total sum as well. Equal the total sum for the initial being equal to final being equal to the total sum of the initial, as we understand very well in the linear case. Now, but the unique thing about angular momentum is that yes, the velocity might not change once it's describing a system, but the moment of inertia can vary, and that can bring a little variation into the expression. And how is that? We know that moment of inertia is subject to the distribution of masses on the surface. Okay, we saw when we're describing it the last class, the rim, where we had three persons staying in the middle and then spreading apart. That distribution changed the value of the moment of inertia. So this is the only point of difference, that the object mass cannot really change, but because of the distribution changing, it can actually affect or influence the value of our moment of inertia, thereby influencing the angular momentum. So if we see the example of the spinning skater, we see that the larger momentum, which is spreading out, okay, from its focal point, brought about the low spin, all right? But when this skater brought everything to a point, it has a small moment of inertia, and it achieved a faster spin or speed. So this is exactly what should govern our idea in solving problems. So let's use the remaining 5 minutes to look at this last slide, which is an example of solving problem with moment of angular momentum. So we have Joey, whose mass is 36 kg, stand at the center of the merry-go-round that weighs 200 kg. So the merry-go-round that is rotating once every 2.5 seconds. So the period is defined because that's the meaning. The period is time taken to complete one rotation, all right? So while it is rotating, Joey decided to walk towards the edge of the merry-go-round, and they walked a distance of 2 meters from the center to the edge, okay? The question is, what is the rotational period of the merry-go-round when Joey gets to the edge? Okay, now in chapter 7, we gave you a table and we emphasize that different shapes have different value or equation for moment of inertia. For a disk, the moment of inertia is given as F I, that's moment of inertia for this, half mass radius square. You know that the formula for moment of inertia ordinarily is this, right? Okay, so from that understanding, we have this value, this, which I said that if we have to give you a question, we'll state this in the formula sheet, giving you, or if we change the shape, if it's not going to be a disk, we'll also tell you in the formula sheet the moment of inertia for that shape. So different shapes have different equation for moment of inertia. So with that understanding and the idea of the linear, we want to proceed to solving this problem that said we should look for the period of the merry-go-round by the time Joey walks to the edge. So let's see the representation at the initial. When Joey was at the middle, the initial period was given, the mass of Joey was given, then the radius from the distance walked to be 2 meters. So we have the angular momentum, initial angular momentum being, we have two objects now, Joey and the rim or the merry-go-round. the sum for Joey plus that of the merry-go-round. So we see Joey at the beginning, that's 0. It has mass. Okay, so the radius at the point is 0. So that's what made this place 0. Okay, so which made the whole expression of Joey to be 0. Plus moment of inertia for disk, that's the value here, times the angular velocity, which gives us this last expression. Okay, so for the final, we also have the summation of Joey and the disk. So for final, Joey has moved to the edge. So we'll have MR for Joey times MR squared, which is our I. We're doing IW. And we're already using MR to represent, or the equation of moment of inertia, substituting into I and W. So I equal to MR squared and this W, or omega. Permit my mistake, please. I always tend to call it W. So we'll have this for the final expression. So if we apply the moment conservation of angular momentum, which is angular momentum final being equal to initial, we have this equation being equal to this, and that is what we expressed here. So we see that R is common in all, so we can bring out R here. So we'll have an expression like M plus half capital M bracket big R F being equal to capital M WI. So this R can take off this R. So if we cancel out the R and we'll make WF here the subject of formula, we'll arrive at this. Now, if you happen to have this kind of question in a test, I expect you between here and this, we'll have 3 lines where we used to arrive at this. You show you're working, don't jump, because the score between this place might be just 4 out of 10 if this question happens to be 10 marks. So show you're working when this kind of question appears. All right. So we just substituted our values into the obtained parameters. And then we also know that, remember this formula from the definition of the period. Okay. So we'll have the W initial being 2 pi over T, 2 pi, which is 1 complete revolution, and the time taken for that. So obtain 2 rad. I'm already eating into our time. I apologize. This is just the last slide, okay? So the final velocity for this, M for the merry-go-round, M for the merry-go-round, and the small m for Joey. Applying it directly, we'll have our initial angular momentum obtained from this expression, and then we'll have our final answer, which is the final angular velocity. And the question said we should look for the period. The final period, therefore, is going to be, we just made, F final is equal to 2 pi T final. So we made this one the subject of formula. That's how we got this. And then we have already obtained the angular velocity final to arrive at 3.4 seconds. So by the time it completed 1 revolution and it's already going towards the second, that is 2.5. That tells us the exact position of the merry-go-round by the time Joey got to the end. Okay. All right. Let me see. Somebody asking.
Can you post this after the class, please?
It's updated. It's
Let me
updated.
check.
Check. Yep. It is. I made sure it's updated because The last time I thought it did, but it did not. So this time I had to confirm that. So check and let me know, please. Okay. Somebody's asking, does that mean week 5 and week 7 are due on Monday? Yes.
Oh, we're still in the week 9. Is that what it is? I thought we were on, I thought this was a different topic. That's why I asked, but I see it.
No, this is the concluding part of the chapter 9. So
Okay. Okay.
yeah, the
Okay.
document
All right. Yeah, I see. Okay. Thank you.
is updated, right?
Yeah. Yeah. It's updated.
Okay.
Okay. Thanks.
You're welcome. So,
I have a
mhm.
question.
All
So
right.
does that mean that week 5, 7, and 8 are all due Monday?
Yes.
Okay, thank you.
No, week 8. No, one is not Monday. There was one I said, I'm giving you time to do it because I didn't post it as at when due. So that one will be after your midterm. We'll submit that.
Yeah,
Okay?
because I noticed that week 5 and 7 both say that they're due on November 5th, but the only one that doesn't have a due date is week 7.
Yes. And that's because I did not post it as at when due. So I'm giving you enough time to do it. Okay? So it
Oh,
will
okay,
not
so
crash into.
yeah.
So we're meeting for the revision class, which is just going to be 1 hour or even less than 1 hour. We'll use 15 minutes to do kind of what we're going to be doing is some of the solution to the assignment and also some comment about what to read. Basically, what you'll be reading for the test is where we stopped or where we started after the test 1 to the immediate. Okay. Which is
Okay.
You go.
So that means that the only one that is due until after the midterm would be week 7.
yes.
Okay, thank you.
You're welcome. All right. So
I have a question.
okay.
So for meeting today, like for our lab, is it just through this link again or what link?
The same link.
Okay, thanks. Just wanted to clarify.
Okay.